Hello, my name is Bruno Bauwens and I will talk about computability properties of the normalized algorithmic information distance. This is work with student Ilya Blinikov and we are both from the Higher School of Economics. Given two discrete objects, we want to express how similar these objects are using some real number between 0 and 1. In fact, we want to express how different these objects are, because for similar objects the value should be close to 0 and for independent objects close to 1. We want to do it in the most general way without relying on any probability distribution or any other assumption on the strings. We will use Kolmogorov complexity, which is a measure of the information in the bit string between 0 and the length of the string. So more specifically, the conditional Kolmogorov complexity of a string x given a string y is the minimal length of a program that maps y to x. The unconditional complexity is obtained by choosing y to be the empty string. We will use an optimal programming language, which means that no other programming language can provide descriptions that are shorter by more than a constant. The normalized distance is defined by this expression. It's the maximum of the conditional complexities divided by the maximum of the unconditional complexities. If strings are long enough, then this ratio is always between 0 and 1. For similar strings, both conditional complexities are small and the value is close to 0. For independent strings, the value is close to 1. To justify the name, we notice that the triangle inequality is satisfied up to very small terms, and they vanish when the strings x and y are sufficiently complex or sufficiently long. The distance is not computable, and our first main result states this in the strongest possible form. We first explain that the function is limit computable. This means that there exists an algorithm that on input x and y outputs an infinite sequence of rational numbers that converges to the distance. A trivial limit approximation, so also Kolmogorov complexity is limit computable. In fact, it's even upper semi-computable, which means that there exists a function g for the Kolmogorov complexity that's non-increasing in t. So the trivial limit approximation of the distance is obtained by replacing the complexities by upper semi-computable approximations. Note that if the normalized distance was computable, we can find a special function g that is constant in t, so g converges immediately. So our main result about incomputability will state that convergence happens very slowly. And in fact, we will consider functions that converge to some value that differs at most by some error epsilon from the distance. For example, consider the function g equal to the constant 1/2. So it will make some error, and this error is at most 1/2. Our first result says that even if we want an error that's only slightly better than 1/2, then the function g must oscillate a lot. So here is the result. Let us consider it. So if epsilon is strictly smaller than 1/2, and if the limit of g is differs from the distance by less than epsilon, by at most epsilon, then we know that this sum must grow at least logarithmically with n. So if epsilon is strictly smaller than 1/2. This result implies all previously given incomputability results of the distance. For example, if the distance were computable, then this sum could be 0, and this is forbidden by the by the logarithmic lower bound, provided epsilon is strictly smaller than 1/2. In the paper 6, it was shown that the distance is not lower semi-computable and upper semi-computable. This is a consequence of this theorem as well, if G was monotone in T, then this sum is bounded by 1, and again for epsilon strictly smaller than 1/2, this is not possible by this result. So in fact in 6 something stronger was shown. It was shown that for every lower semi-computable function must differ from the distance by at least 1/2, or at least something that by any value arbitrarily close to 1/2. And for upper semi-computable function, this result was shown with error log n divided by n. So this result improves the result for upper semi-computability as well to the constant 1/2. For the trivial limit upper approximation, this sum is 2 natural logarithm of n plus a constant. So that means that for a fixed epsilon, this lower bound is optimal up to constant factors. So this result also suggests that if we want to compute the normalized distance, then we can do not better than just approximate the Kolmogorov complexities. The main result of the paper 7, you see below, is that the normalized distance does not belong to the difference hierarchy defined by Selivanov in 2004. So more precisely, for each pair x and y, let us consider the infinite sequence of rational numbers. Any sequence can be viewed as an alternation of non-decreasing segments and non-increasing segments. So the number of oscillations of the sequence is just the number of alternations. So the result in 7 says that any limit approximation of the normalized distance must have an unbounded number of oscillations. And they end with the question, can we quantify the number of oscillations in terms of the length of n? One can observe that for the trivial limit approximation of the distance, recall that's the one where we replace complexities by upper approximations, it has a linear number of oscillations. So there is a big gap between the lower bound super constant and the linear upper bound. This theorem already provides a logarithmic lower bound, because for each oscillation this sum is at most 1. So that means we have at least log n oscillations. And we can increase this further. We show that for any limit approximation of the exact value, and this is the same assumption here, the number of oscillations should be at least linear, almost linear. So there is an extra log n factor, and we know how to get rid of it, but it's a lot of work to write it out, and it will appear in the journal version of this paper. The second message of the paper is intended to mathematicians that want to prove something about Kolmogorov complexity. If your proof is complicated, you should use games. We will give a short high-level explanation about what is the game technique and explain why it's useful. We will mainly focus on plane complexity. Plane complexity can be characterized as the minimal upper semi-computable function that satisfies the following condition for all k, this condition. On the other hand, every mathematical statement that involves quantifiers can be viewed as a game. There are 2 players. One player is called a skeptic, and he selects the variables of he selects values of universally quantified variables, and he tries to disprove the statement. The other player is called the prover, and he selects values of existentially quantified variables, and he wants to prove the statement. The idea is that skeptic selects some nasty instances, and prover needs to construct the required objects. So proving the theorem is precisely the same as proving a winning strategy for player prover in the game. Now let us combine both observations. Given a statement about Kolmogorov complexity, we use the characterizations above to transform it to a statement with quantifiers over compression functions. So in many cases we get a statement of this form. For all compression functions satisfying some properties, there exist other compression functions satisfying the requirements of the theorem. So we need to come up with a winning strategy for the prover in order to prove the theorem. Let us now define an online version of the game. So note that an upper semi-computable function is a dynamical object. So the compression function needs to be upper semi-computable, and we know it's a dynamical object, values drop over time. So skeptic may present a partial construction of the object, and prover will reply with also with a partial function that satisfies the condition of the theorem. So skeptic lets a few values drop, prover should also let a few values drop. And afterwards, skeptic may again decrease some values, and prover may also decrease some values such that the conditions are again satisfied. And at first one might think that it's more difficult to come up with a winning strategy in the online game. But mathematically, both games are equivalent. Especially if the games are finite, then both versions are equivalent. And if they're not finite, there is some computability restriction, but in practice it's not a problem. So now we can consider the special case where skeptic just decreases the value of at most one string in one round. Again, this variant is equivalent to the other games, but it's much easier in this setting. Typically it's much easier to describe a winning strategy for prover, because you just have to react, just need to react on one single string. So in the offline case, where people present the full compression function, one needs to specify a huge object, and the strategy contains many cases that are splitted over complicated sets of strings. And if there are several time steps in the construction, then the number of cases become huge and the proof becomes very long and technical. But in the online case, you just need to react on a specific action for one string, and the strategy becomes much easier. So another advantage of the game technique is that once you define a game, you can think about optimizing the formulation of your game for your strategy or what you want to prove. For example, if you use plane complexity on n-bit strings, you can work with a grid that has n rows and 2 to the n columns, and place tokens on the grid. So the compression function of a string x, so the value of a compression function of a string x now represents the row index of the lowest token, the minimal row index of a token in the column corresponding to the string. So of course there is a rule for the tokens that are placed on the game board, and this rule corresponds precisely to this condition. Games are a great way to involve students in research. The supervisor determines the game corresponding to some interesting open problem, and then the students searches the winning strategy. Students are typically very good in finding winning strategies. And this is how we have proceeded in this paper. So the winning strategy was found by Ilya, and when he was a third-year student for the coursework. So it was not even in the context of a bachelor thesis. And recall that this strategy implies the main result of 7, which is a paper written by 3 senior authors with more than 2 decades of experience in the field of algorithmic information theory and computability theory. Okay, of course these are high-level explanations, and to really understand what is a proof technique, I encourage you to look to some basic examples in the paper 9. It also contains some more advanced examples, and the paper 8, also the game technique was very useful to prove some result about complexity of complexity that was actually used in 6 and thus related to this paper. Thank you for your attention, and see you in the discussions of CSR or any other discussions.